Today is a brief introduction on forces. So this is the start of Unit 2. We're going to look at two different types of situations, dynamic states and static states. Forces you would have seen in Science 10 briefly, so there shouldn't be too much new for you, just more of a refresher from a couple years ago. So if you remember from Science 10, a force is a push or a pull. So there's two different main types. There's your contact force and there's your field force. Contact forces require some kind of physical touch between two bodies. So I've got a couple examples there, like kicking a ball, throwing a ball, pushing on a desk, pulling a wagon, pulling a spring, pulling a cable. Those would all be contact forces. Whereas field forces don't require any kind of physical push or pull. So the example there would be the attraction between a positive and negative charged object, magnets that attract other magnets or iron, if you will. So magnets in general don't require an actual physical touch. They would be action at a distance type of force. Another type of field force would be your gravitational fields created by just masses warping space and time. Or if you want to just go back to the 1700s when Newton came up with the idea of gravity, mass just attracts mass. That's good enough for most purposes. So those are your two main types. But breaking it down in the next few classes, we're going to get into states that are static. And so when you have a static state, that means it's in a state of equilibrium. There is no acceleration. So the body's either at rest, not moving anywhere, or else it's undergoing uniform motion. So that would be traveling at a constant speed in a single direction. It's not turning left, right, it's not going up a hill, going down a hill, not going up in the atmosphere. It's just moving in a straight line with a steady speed, so no acceleration. That would be a steady state. So statics, just think of a sign hanging, for instance. That would be a static state. It's not moving, it's just suspended there, no acceleration. So we'll look at that situation in a lot more detail in a couple of different lessons coming up. A dynamic state is where you have an acceleration. So you have a bunch of forces involved causing a mass to accelerate. So the acceleration is not zero, and all dynamics really is referring to is how things are changing. So this is the study of the causes of motion. So kinematics is all about just motion itself. Dynamics is looking at the causes. So that's investigating the forces involved and the masses involved that's causing the acceleration. So from grade 10, you might remember, you might not. The equation for force comes from Newton's second law, and that's just your net force is equal to your mass times your acceleration. So mass is just a scalar value, so it's not going to actually affect the acceleration or the, it's not going to affect the direction of the acceleration, rather. So your force, if there's only one force involved, it's going to be in the same direction as your acceleration. Right? We measure forces in something called a Newton, and a Newton is just a kilogram meter per second squared. So it's just combining the units from the mass and the acceleration. So now there are four fundamental forces of nature. In this year, we're going to look at just two of the different types. Three if you really want to make an argument for it. But we're going to look at electromagnetic forces, and that's going to be in Unit 4. We're going to be looking at gravity all throughout, but we're going to really specifically focus on the laws of gravity in Unit 4 as well. But we are going to be working with weight and whatnot, and so we will be seeing gravity. The weak fundamental force would be your the force involved with beta decay. So keeping the electrons and neutrinos in with their actual atoms. The strong nuclear force is given the name strong for a very specific reason. It is literally the strongest one. So it's keeping the nucleus together of any atom. Okay, so if you look at their relative strengths, it goes strong is obviously the strongest because we like to be simple about how we name things. Electromagnetic force ranks in second. Its range is infinite, whereas the strong nuclear force, it only has a very, very, very small range. Once you get past, I think, element 83, bismuth, the strong nuclear force is not strong enough because the nucleus of the atom is far too big for it to actually be considered strong enough altogether. So there is a limitation on range. The weak nuclear force is a little bit weaker than electromagnetic force, so you can see the relative strength. So that one's a fraction, this one is a million versus the strong force. And then, of course, gravity being the weakest of all the forces. Very, very weak in comparison to the other ones, but its range is infinite, and the gravitational force actually holds our entire universe together. That's really all I'll spend on this. This comes from Hyperphysics. So Hyperphysics is kind of a web page that gets a lot of people through university. I recommend you go to it every once in a while when you're trying to learn a new topic. If you think I didn't do a good enough job, or if something you just need something more, definitely go to Hyperphysics. Pretty much has anything you'd ever need. So definition-wise, the forces that you'll be working with in the near future would be your friction force, your normal force, your applied force, your tension, and your weight. So real briefly, friction is just the opposing force. So it's always going to be negative. Even if it's written down as a positive value. If I say, for instance, force of friction is 5 newtons, right? When you put it into an equation, you have to just remember that it should be negative. That's all. Drag it's similar to friction, except we call it air drag or just drag in general when we're in some kind of a fluid. So obviously, we'll call it air drag if you're in the atmosphere. If it's in some kind of fluid like water, liquid fluid, if you will, then we would just call it drag. But it's very similar to friction. It's just a resistance force. Friction involves two surfaces in contact. We'll look at this in far more detail later. But for right now, all you just really need to know is that it is always negative. It's going in the exact opposite direction of motion. The normal force is perpendicular to the common surface. The reason why an object won't break through the table is because the table is pushing up on the object with the exact opposite force of the weight. So it's always straight up on a flat surface. Your applied force, this is going to be a just random force acting on any object. So sometimes we'll call it F-apps, sometimes we'll call it FA, or sometimes we'll just call it force 1 or force 2 or force 3, depending on how many forces there are involved. So that is all your applied force really is. So the physical force that we're typically referring to at the time. The tension is the term we're probably going to use when we start talking about ropes or chains or something that is tight, if you will. And then weight is your downward pull of gravity. So weight has its very own equation. So if I start talking about weight, I am talking about the force of gravity. Don't call it W. I know online some web pages like to say weight is W, and that's confusing later on because we get for energy units, work is W. So don't call it W, please. It's just gonna be a confusing next unit when we start getting into energy. So weight is just your force of gravity, F with a small subscript G. So that's different than this G here. This is actually your 9.81 meters per second square. So you probably will remember this from last unit, so don't bother writing it down. And again, your weight is always going straight down. So when you combine forces, maybe this has happened to you, maybe not. Your vehicle's out of gas or whatever, it's just not working. And so, or maybe it's stuck and you're just trying to get your buddies to help push you out. You would actually have to combine all the forces to find your net force. Your net force is the sum of all the forces. So if we're being simple about it and we just have one person pushing forward and then we have your resistance, so your friction of the ground acting against you, you'd have to overcome that friction. This applied force would have to be greater than your friction before it would start to accelerate. So this comes from Newton's second law, which I'll go over in detail in next video. So more appropriately, your net force is just the sum of all the forces, applied forces that are acting on the actual mass, which equals your mass times your acceleration. So in this case, we have 1, 2, 3, 4, 5, 6 gentlemen pushing this truck, and this truck is on the road, so it's probably providing some kind of resistive force going backwards. So if when I add up all 6 of their forces, I'd have to add on the friction as well. Now, I always add forces, even though I know friction is going in the opposite direction, but I know friction is a vector. So if I actually know the number, I put the number in as a negative number. So if I happen to know I have minus 100 newtons of force, I just put that in because you can add a negative. Right? So don't forget that. Friction is always a negative number, but we always add our forces. We add all forces together. So let's just do a couple questions. We'll start off with a nice easy one. So what is the acceleration? What will the acceleration be if there is a net force of 16 newtons on a 4 kilogram mass? So this one's just kind of a freebie quickly to do it. I'm just going to find the scalar value, so I'm not going to bother with vector symbols because it's fairly rudimentary question. This question is looking for the acceleration, so starting with the basic generic equation. If there's only one force acting, then it's just F is equal to ma. So you just divide both sides by your mass, and you get the equation for acceleration to be your force divided by mass. All right, plug in your two numbers, 16 newtons divided by 4 kilograms, 16 divided by 4. You can do that in your head pretty easily. But this next step, I just want to really point out and drive the point home that a Newton is a kilogram meter per second square. Right, I won't always show this step, but I do want to really point it out that when you take a Newton, you divide it by a kilogram, your kilograms cancel off, and you'll be left with a meter per second square. For questions like this, it's not really that important to point out those units, but next unit, in unit 3 and in unit 4, some of your units get a lot more confusing, and you'll need to be able to break a Newton down into its kilogram meter per second square component parts, just as a heads up. So you just finish the math and you get 4.0 meters per second square. I'm not bothering with direction, doesn't really provide me much direction. It's just assume that if you only have one force that's known, it's going to accelerate in the exact same direction as your force. We just know what that is for this question. So we found the scalar value of it. Okay. So moving forward, question 9 in your note package. I forget what page it's on. We have a skydiver complete with parachute, has a mass of 70 kilograms. A short time after the skydiver jumps from the aircraft, the force of air resistance acting on him is 520 newtons. What is his acceleration at that instant? So it says he has a parachute, but it doesn't say the parachute is deployed. So there's a lot of stuff going on in this question. First of all, we know that we are solving for acceleration, and we have at least one force given to us in numbers, so we know that our net force is the sum of all forces acting on the mass. That's equal to your mass times your acceleration. So if we look at the skydiver, so I'm picking on the guy here because they said it was the guy, doesn't matter, the girl too, could have used the same one. We know that he's got air resistance, so that means it's going to be going in the exact opposite direction. Skydivers will typically fall down. Air resistance, drag if you will, has to go in the exact opposite direction. He's falling down because of his weight, right? So his weight is pulling him back down to Earth's surface. Now that doesn't explicitly say that in the question, so that's what makes physics a little bit more annoying than most other classes. There's things that you're just gonna have to know about. So if you're an object and you have mass and you're on Earth, you're going to have weight. Now, you can argue these guys aren't on Earth, but they're falling towards Earth, and they're falling because their weight is making them do that. So this weight here would be that non-contact force I was talking about. Air drag is technically a contact force because air is pushing against you. It can't move out of the way fast enough. So therefore, it's slowing them down. So going to Earth because of weight. Weight has its own equation. So that's F is equal to mg. So we were given the mass. So mass and weight are not the same thing. We were given the mass, and from that we can solve for the weight. So if you just multiply your 70 kilograms by 9.81 meters per second square, you'd find out that this fellow has a weight of almost 700 newtons, so 687 newtons as far as his weight is concerned. We know that's acting down, but I just saw for the scalar value, so there's no vector symbols above. So now we can proceed. We have two forces. We have his weight and we have his air drag. So we know that since your net force is the sum of all forces acting, I have the two forces involved. I've got weight plus the actual drag, because again, you're always adding the forces. From here, we need to know, well, which way is going to be our positive direction. If we know that our body is moving down, we should probably make down the positive direction, because that would be the direction of the acceleration. When in doubt, try to define the positive direction as whatever direction you're accelerating, whenever you can, if you can figure that out ahead of time. So when you plug the numbers in, I'm going to plug in the number 687 newtons as a positive number. Now, of course, this is slightly rounded in my calculator, but this is a positive number because it is going down. Whereas drag, the 520 newtons defined in the question, is going in the exact opposite direction. So therefore, I'd write it down as negative 520 newtons. So from that, you just add them together. I missed a step. You just add them together, right? 687 plus negative 520 gives you the 167 newtons. And then from there, you would just divide both sides by m because you are looking for the acceleration. So I kind of preemptively did that in my typing. So divide both sides by your mass. On the right-hand side, I didn't bother putting the number in, mostly because I don't have a number there to start with. And on the left-hand side here, I'm just dividing by the actual 70 kilograms of his mass. So 167 divided by 70 gives you an approximate acceleration to three significant figures of 2.38 meters per second squared. All right, just like the last question, we have a Newton divided by a kilogram. I didn't expand the Newton. I just showed you that in the last question, that the kilograms would cancel out and you're left with a meter per second squared. Positive means that he is accelerating downwards. So he's still speeding up on his way down. Hopefully he'll open his parachute soon. So, potato cannon. Typically we blast these off in class at some point in the semester. And every year we determine together as a class that the approximate speed of my potato cannon that I have in the class is often somewhere between 28 meters per second and around 32. So I'm just going to split the difference. One year it was 25, but I didn't have big enough potatoes to fire. So more often than not, it's somewhere between 28 and 32. So splitting the difference, I just happen to know that potato cannon is going to fire a potato out at approximately 30 meters per second. So knowing that, the way these potato cannons work is you plug them full of ether. You can use hairspray, I guess, but I like to use ether. It's a cleaner burn and it has a lot more energy to be delivered. So in this combustion chamber, you light a match, it goes kablooey, and it forces the potato that's in the chamber right here to exit at pretty fast speed. So 30 meters per second is just over 100 kilometers an hour. So my potato cannon has a barrel length of 120 meters, so that's this part in the blue. And by 120 meters, I meant to say 120 centimeters, so 1.2 meters. Apparently my mouth is not listening to my head today. If the average mass of the potato bullet is approximately 400 grams, I only know this because one year we went and did some extra stuff and we did this about 20 something times, and more often than not, we found that the mass of the potato that we put in was somewhere around 400 grams. So I'm just using 400 as a nice round number. So what is the net force provided by the explosive combustion of the ether? So that's a great question. What do we know? We know that it starts from rest at this spot right here. It accelerates over that 1.2 meters, and then it leaves the cannon with a speed of 30 meters per second. So this explosion right here provided a large enough force to cause it to accelerate to 30 meters per second. So that means my net force is equal to my mass times acceleration. There's only one force acting and it's going straight to the right. We're assuming that friction is not significant enough to really measure, and I don't have the values for wet potato on PVC for friction, so I don't know what that friction value would actually be anyway. So I'm going to assume it's small enough to not really matter, at least not at those speeds. So my net force equal to my mass times acceleration. I would like to know what that net force is, but I don't know what the acceleration is. So we have to go an extra step. We need to figure out what the acceleration is, and based on the fact that I've got my distance traveled, I've got my final speed, I've got my initial speed, I'm going to have to use equation number 5. The final speed, or velocity if you will, squared is equal to my initial speed squared plus 2 times my acceleration times my distance traveled. So if I manipulate that equation for acceleration, you would end up with final velocity squared minus, or speed, minus initial speed squared, all divided by 2d. So again, just solve for acceleration. We brought that over to the other side by subtracting, and then we just divided both sides by 2 and d. And that solves for your acceleration. Knowing that it's starting from rest, I'm going to make that equation a bit easier and just get rid of initial velocity. So my actual acceleration in this context is going to be final speed squared divided by 2 times your distance. Now, I usually like to just combine equations because I hate having to use my calculator and stop doing my progress. So typically that's how I do a lot of my math. So when I combine this equation and put it in place for that acceleration, all I'm doing at this point, since I'm taking mass times acceleration, I'm just taking your mass times your final velocity squared divided by your distance or displacement. And at that point, that's when I'd plug my numbers in. Usually I do it all in one big long step in my calculator. Keep in mind that when you square your 30 meters per second, you're squaring the number and the units. So please don't forget to square the units. That's why I have 900 meters square per second square. So the difference between having that square on the outside of the parentheses versus right next to the actual units. So working this through, you'd find that you'd end up with your meter canceling down below, and it will cancel that square that was up above. And now you just have a kilogram meter per second square, which is by definition a force, a newton. So we end up with approximately 150 newtons, which doesn't sound like a large force, but keep in mind we have a pretty small mass. Right, 150 newtons on a 10 kilogram mass would not have that kind of an acceleration. So just keep that in mind. Even though the force is small, we have a very small mass. That's considered pretty large for our context. I'm going to stop there for the video. You should probably try some of the problems. You don't have to do all of them. Just pick and choose whichever ones you want. They vary in difficulty, but there's a bunch of problems between 27 and 30. Some of the problems involve friction. Some of them will involve weight. So you'll just have to remember that friction is always negative when you plug the numbers in. Even if they give it to you as a positive value, remember friction is negative. Weight is always going straight down, so don't forget about that as well. So whether or not you define down as positive or negative really depends on whether or not the object is accelerating. I will stop it there. If you have questions, please fire me an email.